Hello, everyone. First, I want to thank the organizers for giving me the opportunity to present my work. So I will be speaking about fluids of light in disordered environments, which is a work that I'm doing at Institut de Physique de Nice. I think everyone here is able to recognize this picture here, where we have a river and the water is floating and there's a rock in the middle. And so when the water hits the rock, we see this interference pattern that's observed on the water surface. Now, there are people who have been able to reproduce this kind of, the same kind of image in the lab, where they also have a fluid and an obstacle, and they see the same interference pattern that they see in nature. But here we are in the context of quantum fluids. And so by changing the conditions, we are able to completely cancel the effect of the obstacle on the fluid, or in other terms, to be in the superfluid regime. So us at Infini and at other labs like LKB, for example, we have been able to reproduce also this kind of experiment, but with one difference, it's that we are using light. So the possibility of exploring fluids of light in propagating geometry, which is a system where the light propagates along the direction of propagation, has been studied in different platforms, for example, in hot atomic vapors like in LKB, in thermal liquids, and also in photorefractive crystal. So this slide has been repeated twice so far in the conference, but I will just go briefly. So the notion of light hydrodynamics relies on the analogy between the nonlinear Schrödinger equation, or the Grotowski equation, and the equation of propagation of light inside a medium. So the first important analogy is that the temporal evolution of the wave function will correspond to the propagation of a light beam inside a medium. So as the beam propagates in space, each step in z will correspond to a different time t in the evolution of a 2D system, which is the transverse plane of our medium. Second analogy is that photons will acquire an effective mass, and this is because of the wave number inside the material. The last term represents the non-linear response of the material, which is perfectly analogous to the interaction potential found in the Grotowski equation. I want to mention here that the interactions in our system are repulsive, and so we have a defocalizing effect. So as a conclusion, we can consider that a fluid of light is a collective behavior of interacting massive photons. So now that the analogy has been drawn, we can proceed in the same way to derive the hydrodynamical equations, which I will not detail. But for that, we can use the Madelung description, where we consider that an electric field can be written as an amplitude and a phase. To be able to write them in optical terms, we need to consider two important conditions. First one is that the fluid density it's that the intensity of the laser will play the role of the fluid density. Second condition is that the gradient of the phase will play the role of the fluid velocity. Now, it's very intuitive to understand the first condition, as experimentally it's very easy to control the intensity of the laser, but it's less intuitive to understand the second condition. So for that, I will give you a simple example. If we shine light upon our nonlinear medium and we take the gradient of the phase, we can see that it is directly related to the sign of the angle of incidence. So experimentally, if I want to change the equivalent of my fluid velocity, I just have to change the angle of incidence that's of the laser beam that's injected in my medium. We can also define the optical healing length, which is the characteristic length in our system. We can also define the critical velocity that is related to the nonlinearity of our system, and the Mach number, which is a parameter I will be using in a bit. So I haven't mentioned it yet, but The nonlinear medium that we have is a photorefractive SBN crystal, and the nonlinear effect is the photorefractive effect. So what happens when we shine light upon this crystal? We have photogeneration of free carriers, so charges will move around inside the crystal, and they will move due to two distinct effects. First one is diffusion from bright spots to dark areas, which is negligible in our crystal. Second effect is due to an external electric field, which is how we will manipulate it in experiment. So charges will recombine at different location, creating a field inside the crystal, which is the space charge field, which will induce a modification in the refractive index. So experimentally, we have two parameters to control, which is the external electric field and the saturation intensity. And we know how the delta N varies with respect to the intensity. So if we want to compare it to a basic Kerr nonlinearity, we know that it is linear. And so this is valid for relatively low intensities. But then again, at high intensities, the delta N saturates. So, as I said, experimentally, we can control two parameters, which are the intensity of the laser beam and the velocity of my fluid. And so by changing this parameter, we can actually probe superfluidity. This is a study that has been done previously in my group. So actually the best way to probe superfluidity is to come with a fluid and then put an obstacle in the middle and see how the two interacts. So in our case, the obstacle is photo-induced obstacle through the photorefractive effect. And it's very important to have a constant obstacle along the crystal length. So because of the equivalence between time and space, we want a fixed obstacle, and so we want it invariant in Z. So these images are the spatial distribution taken at the output of the crystal. And so in the first image here, so the changing parameter is the Mach number that I mentioned earlier. It is the ratio between the velocity of the fluid and the critical velocity, which is related to the delta N and also related to the intensity. So by changing the intensity and the angle of incidence, we can either be in this situation where we see a diffraction pattern. So the red cross is the obstacle. A diffraction pattern results from the interaction between the fluid and the obstacle, or we can vary the Mach number to a point where we don't see any interaction between the obstacle and the fluid. So after that, my group was also interested in exploring a different regime, for example, turbulence, and this was feasible just by changing for example, the diameter of the obstacle along with the fluid velocity. So now that we have full control and full characterization over our medium, we can even go to a different regime. And so one idea was to propose why not study disorder in the crystal. So I mean, we already know how to inscribe one obstacle, so why not go even further and see how would the crystal react if we create a disorder, a non-diffracting disorder. So for the same reason as before, because of the equivalence, we wanted to create this non-diffracting disorder. I mean, we can take full advantage of the capacity of our crystal since we know how to already inscribe one obstacle. And so from that, we can have many questions that we can ask ourselves. So we already know how nonlinear systems work in homogeneous medium, and we know how linear systems work in disordered environment. And so basically, we want to make the connections between the two. So study superfluidity in disordered environments, because as far as we know, it has been studied in 1D. Theoretically and numerically, but overall everything still remains to be studied in 2D. And from the other hand is to study localized states in the nonlinear regime. So the first step was to actually create this non-diffracting speckle. And the beam shaping technique was to actually use a diffuser to create the diffracting speckle, and then put an amplitude mask to filter out and keep one modulus of the wave vector to guarantee this non-diffracting nature. So here I show you the experimental results at the input and output of my crystal with correlations up to 85%, which was actually an achievement for us. And we saw basically we have this non-diffracting speckle. I want to mention here the ring parameters on which we can play to ensure this non-diffracting speckle. So first point, we want to make sure that we have high correlation between the speckle images along the length of the crystal. Second point is we wanted the grain size of the speckle to be of the order of the few healing lengths. And so we noticed from this graph here that as the width of the ring increases, the correlations start to decrease, and we have less and less, so it becomes more and more diffracting. So after creating this constant disorder, we wanted to make sure that it is well inscribed in the crystal, and for that we can convert the intensity into a delta n and see in what range our delta n is in. So this speckle image is taken for 1 laser power, and so here we see how the delta n varies as function of the intensity. And so for high intensity points, we see that it corresponds to a high delta n of the order of 10 minus 5. For now, experimentally, I'm able to achieve a delta n of the order 10 to the power minus 4. So after having characterized this disorder, we wanted to see how, see its effect on the fluid. So by keeping the fluid in the linear regime, we wanted to see the effect of the disorder on the fluid. And so by increasing the force of the disorder, we noticed that we have some holes creating in the fluid, which exactly corresponds to the place of the disorder, which is in the black points. So the fluid is in the blue, and the dark points are the obstacles, the speckle. Now, one well-established way also to qualitatively see the effects of the disorder on the fluid is to actually look for the emergence of wave localization. So these are preliminary results that I took last week, actually. So the first row is for one realization of the disorder. Second row is for the average over 10 realization of the disorder. And so with increasing the strength of the disorder, we notice that we can go from a diffusive regime characterized by a Gaussian to a more localized regime characterized by an exponential decay of the mean envelope. So here I wanted also to say, one way to actually look for the localization, for a spatial localization, is to focus with a tight beam. And so if the disorder is weak, the beam is more likely to spread due to diffusion. And if the disorder gets stronger and stronger, it will suppress diffusion and will favor localization. So as I said, this is an ongoing work. So these are preliminary results, and we still want to see how nonlinearity affects spatial localization. So that's from one hand. And from the other hand, we also want to see how superfluidity is affected by the disorder. And that's it.